Let's do some arithmetic with vectors in 3 dimensions. So in 2 dimensions, we did addition, dot product, projection, and finding the angle between 2 vectors. And these were the ideas that we saw. We would add the components, add the parallel components for addition. For the dot product, we would multiply the parallel components and then add them. For projection, we take the dot product and divide by the magnitude of our goal vector squared, and then multiply by our goal vector. And lastly, we took the dot product over the product of the magnitudes and took the arc cosine to find the angle between them. So these ideas all scale very naturally into 3 dimensions. For addition, we're just extending it. So x1 plus x2, y1 plus y2, and z1 plus z2 is the three-dimensional addition. Same thing with dot product. x1, x2 plus y1, y2 plus z1, z2. All what you expect. For projection, the formula is identical to what it was before. The dot product of v and u, now the dot product looks like what's in green. The magnitude of u squared, we talked about that before, times u. And then for the angle, each of the individual pieces are different, but the overall thing is still the same. The dot product is now the 3-dimensional dot product. The magnitude is the 3-dimensional magnitude, but everything is identical. So these ideas, it's just a natural extension. You should be aware that we can extend them naturally. So let's say that this is the vector v, this is the vector w. Let's say I wanted to find the dot product of these two. Well, first we should simplify each of the separate vectors. So that vector and that vector. So 5 times 2, 3, negative 6 plus 2 times 1, negative 6, 0, dotted with v, 2, 3, negative 6, minus 1, negative 6, 0. Multiply these together. We have 10, 15, negative 30, plus 2, negative 12, 0. This we want to distribute that negative in. 2, 3, negative 6, plus, and this is just an example. We could do a lot of different types of vector arithmetic problems, but this is just an example of what we could do. And all the process is still the same. Add the parallel components, so we get 12. 15 minus 12 is 3, and negative 30 plus 0 is negative 30. Dotted with 2 minus 1, 3 plus 6, and negative 6 plus 0. Now we multiply the parallel components. 12 times 1, 3 times 9, and 30 times 6. Add these together, and I'm getting, I believe, let me just do it piece by piece. Add these two. 12 plus 27 is 39, plus 180 is 219. If we wanted to project one vector onto another, this is written, the projection onto 4, 8, negative 1 of 30, 0, 0. So this is our input vector, and this is what it's being projected onto. So this is kind of like the base of a logarithm, that it's part of the name of the function. It's a projection onto this, and this is our input. So what it's saying, if this is our u, this is our v, we want v dot u over magnitude of u squared times u. V dot u is 30, 0, 0, dotted with 4, 8, negative 1. This is u dotted with itself, or the magnitude squared. So that would be 4 squared plus 8 squared plus 1 squared. And then all at the end, we're going to multiply by 4, 8, and negative 1. So dot these together. 30 dotted with 4 is 120. Plus 0, plus 0. And this has become 16 plus 64 plus 1. 4, 8, negative 1. 120 over 16 plus 64 is 80. 1. And I don't think this is going to become any simpler by multiplying it in. If you want to multiply it in, you can, or you can leave it like this, depending on what the question is asking. So I'll just multiply it in because some of you like seeing it that way instead. And that would be 480, 81st. 8 times 12 is 96, I believe. Yeah, 960, 81st, and negative 120, 81st. Yes. So this is how we project a vector onto another vector. Everything is pretty much the same as before.